1 minute. Okay, share. Yeah, do you see it?
Perfect. Now we can see it. Yes.
Yeah,
Please put it on full
okay.
screen and set your laser pointer, and then we can start.
Yeah, okay. And if I click you guys away, uh, yeah,
All right, that's perfect.
no, I can still see you.
Thank you, Anita.
Yeah,
All right, so welcome everyone to the EMS webinar series. We're going to dive straight into our next topic. And our speaker today is Dr. Anita Buekenhoudt. Anita graduated in 1983 at the University of Antwerpen as Master in Physics. Then she obtained a PhD also in physics at the University of Leuven. After a 2-year postdoc, she joined the Flemish Institute of Technological Research, VITO, and she has been working there as a project manager, senior scientist, and a membrane team leader for more than 3 decades now. Her work focuses on the development, characterization, and application of porous membranes in a broad range of challenging liquid separations in the chemical industry. Her team develops new processes and own innovative ceramic membranes supported by data-driven modeling, all in collaboration with several universities and industrial partners. She has attracted and managed numerous national and internationally funded R&D projects and contract work for industry. She authored over 100 publications, 5 book chapters, gave 100 international presentations, and she is the inventor or co-inventor of 11 patents. So before we start with her research presentation, Anita, we would like to get to know you a little bit. And we are glad that you agreed to discuss a couple of topics that are usually not covered at conferences and workshops.
yeah,
So the
that's
first
fine.
question is, where do you come from? And how did that environment influence you to become a researcher? If you could share your thoughts on that, that would be great.
Yeah, I think in me being a researcher, there's a lot of influence of my father. My dad was actually a chemistry teacher, and he brought, let's say, the interest in scientific topics and the curiosity of a lot of phenomena. He brought this from a very young age already to the family. I remember that, for instance, you showed us when you were very young, when you are running with a ball and you toss it upsides, that the ball is following you. And that is actually quite weird. So he pointed to this type of things. And I think from there, it triggered my scientific interest, and that's how I started studying physics. I thought a little bit of going for engineering, but I think the fundamental part of it, the understanding part, is also quite important for me. That's how I studied physics. Uh, I think I studied when I started studying physics, I already had in mind not to teach, but to be a researcher. And but I had to learn it also, and I had some good mentors around me. Yeah, both in master's period and in PhD period. So that's how I ended up 35 years later here.
Okay. And most of the membrane scientists, they usually study chemistry or chemical engineering, maybe mechanical engineering, but not really physics. So are there any specific areas in physics that you're still capitalizing on and then you can kind of take advantage of during your research?
I think, of course, in membranes, I will have the synthesis, often the application in chemistry. It's of course very chemical, and there I miss a bit the way of thinking of a chemist. But luckily, I'm surrounded by very good chemists, and I've been collaborating with both organic and inorganic chemists in this way. And this is very important, I think. Now, but if you think on transport chemistry, transport phenomena, this is of course much closer to how a physicist looks at things. I think a lot of physicists also think in pictures. We like to see things, to be able to visualize things, to make things schematic. And I think it's also very, very helpful in doing membrane science. Yeah, as to modeling in general, I think we, as a physicist, I have also a good affinity with mathematics, I think, and this is closer. This part of the work is, of course, closer to us. But the thing is, good collaboration in order to, yeah, and have good exchange of ideas, and then you can have the full pictures because both chemists, also computer scientists, physicists, they all look at the same problem in a little bit different way. And it's combining these different views that can give you a really nice understanding. And yeah, that you cannot get when you look at it on your own.
Mhm, mhm. Thank you. And you mainly focus on inorganic membranes and ceramic membranes. So,
Yes.
in your opinion, what are the main challenges in inorganic membranes nowadays? You can also mention in general what are the main challenges, but also in particular for inorganic membranes.
Yeah. Yeah, but my kind of affinity for the ceramic membranes, of course, also comes out of my physics background. I think this is more natural understanding for me. Of course, there is still a lot of chemistry around. But that's why I've been always and focusing a lot on the ceramics. Uh, I think, yeah, you do not have to apply the ceramics in areas where the polymeric membranes are doing their thing very well. Because, yeah, the economics are just completely different. In the synthesis of these membranes, they rely on high temperature. Um, and this is definitely the weak point, I think, one of the weak points, let's say, of the ceramics. The other weak points for the moment, you have, of course, like the very dense zeolitic membranes, but also difficult to upscale. These are quite dense and are used in gas separation or evaporation. But the yeah, for the liquid filter, the other liquid filtrations like nanofiltration, for the moment we're still a bit in compared to polymeric membranes, we're a bit on the higher pore size. You can change the surface chemistry. I'll show some examples later, and many other people have been doing nice work on this. So that is not an issue. But making them with small pores and upscalable without defects, that is still and cheap. There are a lot of things going on using cheaper materials, bringing down the sintering temperatures of the supports. So there is a lot going on. to tackle these issues, but we are not there. So it's, in my point of view, best to use these membranes where their robustness, chemically or temperature-wise, is of very much importance. And there are a lot of these applications around.
Okay. So I think based on the title of your talk, you will elaborate on all of these challenges and probably the achievements so far in the field.
Well, I will give a few examples of what we have been doing lately and even a bit earlier, but I focused a bit on the latest, on the recent results that most of you probably never saw before. So,
Okay, great. So you've been working in this field for more than 30 years. It's a long time in membrane science. So what is your advice for junior researchers working in the field of membrane science?
um, yeah, I would say in general, for junior researchers in general, not only membrane work, I think doing research can be sometimes very frustrating, and you get a lot of technical things that don't work well, or results that you do not expect, negative results. So I would say embrace these frustrations, because sometimes, and think about negative results, unexpected results, as results on itself, because that's what they are. And often we can learn much more from these, from the things that didn't work well, than from the things that worked well. And it's a bit a pity that in most presentations, in conferences, you never see these things that didn't work,
Indeed.
um, although they give us a lot of insights, I think. Now, particularly on the membrane work, um, yeah, a bit what I already answered in the previous question. It's it is membranes research is a very interdisciplinary, multidisciplinary topic. So do use this. Look for collaborations. Look for people with other views, with other expertises, and it's the synergy of this collaboration often that gives you the magic, and that gives you ideas for very innovative ideas that you otherwise cannot come up with. So I think this is quite important.
Great,
At
thank
least,
you. I couldn't agree more, especially with the first one on the negative results and their importance. So lately we work a lot in data science and machine learning, and as you also know, it's super important to have negative results as well.
yeah.
Okay, maybe one final question. So, what do you find the most fulfilling in your job?
Oh, I've always liked my job a lot, and there's different things that are very positive. I think our way of working as a researcher, as development people, it's very diverse tasks that you do. You do experiments, you do interpretation, sometimes analysis. You have to report this in a good way, find ways to present it so that other people can understand, have to write proposals. Of course, I must say that that part, I think we spent a bit too much time there. That could be spent more on doing research itself. So that is one part which is nice. I think, of course, it's nowadays very international, so you get to see also other countries. You get to know other people from other cultures. That is very nice. I find very nice myself. Um, uh, as and then as let's say which gives you a good feeling, which is very fulfilling, is when you have projects with industrial partners where things go well, sometimes after tackling quite some challenges. But when it ends very positive and industrial partners are very happy with the results, this is particularly has been particularly fulfilling for me.
That's great. I mean, it really came across from what you said that you enjoy what you do, even after 30 years being in membrane science. So I think that's also motivation for the younger scientists listening to you today. Uh, Thank you for your thoughts. So now let's move on with your research presentation with the
Okay.
title Applied Membrane Research for Chemical Industry, Technical and Economic Feasibility, Scalability, and Predictability. So
Yeah.
Anita, the stage is yours, and once the presentation is over, then I will read the questions from the chat, and then we can go through the Q&A part together. Thank you.
Okay.
It's yours.
Thanks, Georgie. No, at first, thank you very much for the invitation. It's nice to be able to share some thoughts and share some results with you. Okay, just a few words. Maybe some people that are listening now don't know VITO. VITO is the Flemish Institute for Technological Research. So we are located in the north of Belgium, in Flanders. We are about 1,300 people right now, and like I think all institutes nowadays, very, very international. And at VITO, we work on sustainable solutions in many different topics, in many different aspects. Now, one big part of what VITO is we do actually applied research, meaning that we work together with universities, looking often more to the fundamental research and working on the other hand together with industry to find solutions for real industrial problems. This makes, of course, also that we typically work at higher TRL levels. So let's say from 3 to 7, we come already to pilot scale of demonstration. Now, when you look at the definition of applied research, is of course it's triggered, it's driven by real industrial problems or societal problems, and it's often depicted in this square where we are actually in the Pasteur quadrant. So it's, of course, we are triggered by the use, but to be able to fully implement and flexibly implement a solution, it's also very good to have quite some fundamental understanding. So it's not research for the curiosity alone. It's driven by real problems, but trying to understand enough. Now, of course, when you work with the industry, it doesn't stop with experimental feasibility. You also have to show them that it works at long term, it is a robust process in bigger scale, and that it's also economically feasible. Because if it's not feasible economically, when there is no value there, it will never be implemented. And on top of that, it's very interesting when preferably you are able to model your solution, the process, or to model the transport of a membrane and to predict it. That helps to implement it in industry. So I'm working, this VITO in general is working in this way. I'm, of course, working in the membrane group that is in the membrane team that is nowadays called MESH. And our current focus has been on liquid separations. I guess in the future we will go back to also partly gas separation. We did it in the past. But for the moment, and my presentation is focused on liquid separations. Of course, we all know that in chemical industry, there's a lot of separations around, and these separations cost a lot of time and money. And they're mainly done now by thermal processes. So replacing them, being able to replace part of them by membranes would lead us to a much more greener chemistry. Now, when we look particularly to separations in chemical industry, you're often there with very small molecules that need to be removed or fractionated. So we come and we focus a lot on the tighter membrane processes, being organic solvent nanofiltration. That's been focused from the start of this process, actually, perforation, and a lot nowadays, a lot of membrane contactors, both membrane distillation, but also membrane extraction. Where we work with all types, a variety of sectors in the chemical industry, from oil and gas and base chemical producers up to more fine chemistry, and a lot with pharma. We have been working a lot with G&G. Janssen Pharmaceutica is really nearby us, so we did quite a lot of projects with them, and also a lot of biotech nowadays. Of course, we look at separations and replacing these or adding membranes there in every aspect of the factory, not only the reaction where we try to add a membrane to come to process intensification, but of course also downstream, solvent recovery, side stream processing, product recovery from the downstream and from the side streams. So we look at membranes everywhere in the chemical process. We've done projects all over. So it also means that we do not only look to membranes on itself for purification, concentration, solvent recycling, but also by hybrid processing, for together with distillation to debottleneck distillations, or solvent recycling before an extraction step, or solvents swap before a lyophilization. These are a few of the examples we did. And then what I already said before, this integrated separation where we really couple the membrane to a reactor. And so we can shift the equilibria, we can avoid side reactions. We did a lot on high dilution reactions to improve the solvent use. And we did also a lot in reusing the catalyst for a longer time in the same reaction. So in other words, that part gives you the possibility to produce more with much less. Anyway, when you work with industry, there's some specific challenges or requirements there. When you look purely to the membranes, they typically don't like you to work with something you have made in lab and stays at lab scale. They want a solution, so it means they need the membrane that you propose to be commercially available at scale. In our case, we always make our instruments very flexible so that they can work with polymeric and ceramic. Like I explained, I have a particular affinity to the ceramic membranes, but we only use them, of course, when it's relevant to use them. It does not necessarily mean that these are all membranes already on the market. They can also be in-house developed, but there has to be a track. That's what the industry typically asks. There has to be a clear track to bring them on the market. Now, as to operations, you stick in the testing to process parameters that are very close to what you will use when you implement this. For instance, this means if you have a pressure-driven process, you use cross-flow and not dead end. So we actually almost never use dead end at Vito, because we've also seen a lot of differences, especially in solvents. So always cross-flow. When you work with perforation, this means that you work with realistic vacuum. For MD, it means that you work with realistic temperature differences and temperature levels. So anyway, you work with the temperature of the feed like it will be available in the company. Um, Also, the streams, you work with a real stream with all the possible impurities, even trace amounts that are there in the pHs that are there. So, and no synthetic streams. This often sometimes poses problems for the safety issues doing the testing, of course. And as to timeline, time is money. So it means that normally the timelines of these projects are relatively short. So if you look at such a typical project, then it starts, of course, with a membrane screening at like a liter scale. I give here the instrumentation that we have for OSN. We start with the selected membranes, polymer, ceramic. You see here, and is flexible. This allows us to put many different type of modules here. So you see now a single tubular ceramic membrane, but can be also a flat sheet polymeric membrane. Sometimes we already look a bit to temperature differences or the influence of transmembrane pressure. Next step, when you have selected one or two best membranes, you go over to a proof of concept, but you do this already at a bigger scale. And this bigger scale, typically are 5-liter feed vessels. This allows you and a bigger membrane with already in module. So if you think of polymeric membrane, you think of a 2540 or a little bit smaller module, spiral wound module, for instance, which has already the potting material that you can test for robustness. In this study, we do the full process, so full concentration, full diafiltration, this type of stuff. And you look at parameter optimization, and doing the full process gives you also clear options to already assess fouling and, if necessary, cleaning, of course. It gives you also some good values that you could use in first technical evaluation. Next step, when everything goes well and the company, the client is happy, you go to full pilot testing. At Vito, we have 3 of these OSM pilots, and they can be used in-house at Vito or on-site. They've been all over Europe and even the world. And you do the full demonstration over months to see really the process robustness and stability. And it gives you, of course, values that you can use in a full techno-economical evaluation. As OSN is also very interesting for pharma, we decided at Vito to invest also in our pilots being GMP. So 2 of the 3 pilots are good manufacturing practice proof, let's say, following the rules that are applicable in pharma industry. So, and you see here pictures of the pilots we have in different projects that we started from small, from the screening up to the piloting work. The first pilot we had, and we had a very nice project together with DSM. It was the recovery on an API in a distillation residue that they were actually piling up because they knew there was still a lot of money in there, but they didn't know how to take it out. By just methanol dilution and then followed by concentration and biofiltration, we could really recover this API. We did this operation. It was done with salt membranes that they screened themselves. There was a very nice piloting campaign of about 1 year with 24/7 operation, not a lot of difficulties with fouling. So it was really a very successful project. Later on, we did in the Netherlands a project with Bunge, which is an edible oil manufacturer, and we did their acetone recovery in order to intensify their distillation. And here we both tested salt polymeric membranes and our crafted ceramic membranes. I will say a little bit later about our membranes later. This was, I think, the first demonstration of our membranes at the scale. And there was also a good economical evaluation. And third process is really with a pharmaceutical company where we did dye filtration and concentration in order to replace a very tedious extraction. And there we tested both an OSN polymeric membrane and our crafted membranes. And our membranes came up as the best due to actually the removal of the pore fillers, which kept leaking out actually even after a very strong washing of these membranes. So it was also a very lucrative project for us. Now, I'm gonna dig into a little bit deeper into a few examples. Telling you more how we work in detail. So the first thing is on the synthesis of membranes, so customizing surface modification of ceramic membranes in order to create flexibility on the ceramic membranes, which are typically metal oxide membranes with a lot of OH groups on the surface, meaning that they are typically very hydrophilic. So we started back in 2009-10 together with a postdoc from University of Antwerp. We started developing a grafting method based on Grignard chemistry, and we did this not on flat sheet membranes. We did this directly on single tubular membranes where we know that this quality, the porosity, and so on is very similar as the next step, multi-channel membranes. If you do this on flat membranes, it's of course possible, but you will have to revisit your synthesis procedure again because there is so much difference between a flat sheet and single tubes. So that's what we did. With Grignard, we of course work on these OHs on the surface, and we make a very specific direct metal carbon bond, which turned out, and a lot of people were very skeptic, but we dig very deeply into the stability of this bond, and it's on this metal oxide framework actually that you have underneath. This bond is particularly stable. We are able to we are very flexible in what we can make. not only on the type of groups we can put there. You see some of the possibilities that we made over the years, but also in the type of materials we can work with it, the pore size, the materials. It doesn't even have to be membranes, of course. It's possible to work up powders on nanotubes, on flat sheet things. Of course, this has allowed us to what we like to call play with the affinity of the membranes. And we did this in several ways. We had a very good postdoc by Sarah Hossein Abadi, who looked, of course, to solvent filtration. And we were able to show that by increasing the membrane solvent affinity, we get much better performance. And in some cases where we really boost the membrane solute affinity, you can find some kind of chromatography type of performance. And we had about the same time another PhD, Ghulam Mustafa, who was digging into anti-fouling effects of this grafting, and we were able to show clearly that with the metal grafting, with metal grafted membrane, you can have really nice anti-fouling effects, higher fluxes, lower decrease of your flux, and in some cases, even higher retentions. Anyway, we were able to play around with our membrane affinity, and in this way, we were actually learning also a lot about what's happening in solvents and what's happening with fouling. So not in that aspect that we can really predict it, but we got clearly a lot of extra understanding. Now, this is when once we knew actually that these membranes were really, this grafting gave us a very nice membranes, we started to think about upscaling and how to make them in bigger scale. So we started, of course, first with the small tubes in stirring and shaking instrumentation, glassware. But quite fast, we started working in a glove box. Grignard is not the easy chemistry. You have to work in very dry circumstances. So in a glove box and under filtration conditions. This worked pretty well, and we used this glove box actually to extend it and be able to put a multi-channel membrane there of 1 meter 20. And also this, we were able to process very well. And then we went over in 2017 to build a machine where we could make 5 membranes at the same time. So, and then later on, we even upscaled this to 10 membranes, and also being a bit more flexible in the design of the multi-channel membranes we could work with. Anyway, these two last machines gave us, of course, the possibility to produce these membranes for many different pilot campaigns, like I showed before. At that moment, with the bigger machines, we were able to do also a very good economic evaluation to evaluate the cost of this grafting, to determine the factors that are the most important. And something like the dry solvent is very important here. And we could also pinpoint then how to make it even better if you want, how to change the process if you want to make larger amounts. And this has led also to the creation of the spin-off in the end of 21. It's called A-Membranes. It's led by Bart Koen, and he's building out this equipment now to come to really make large-scale production himself. We still have, of course, a good collaboration with all our spin-offs, by the way. That's why I just, of course, A-Membranes is more in the beginning of the first years after creation, but we had earlier very nice transfer projects. And I just mentioned here the zircon separators. This zircon stands for mixed matrix membrane, zirconia particles inside of polysulfone, and they turned out to be very good separators with better performance in alkaline electrolysis. And it's, of course, boosting because of the green hydrogen production. And we have been working for a long time now with AGFA on this topic, and they brought the first generation of membranes on the market in 2007, and they're running more than 100 installations now. They also recently got very nice extra funding to upscale this production of even further generations of these separators. And more recently, we had IPC membranes, internal permeate channels, membranes, backwashable membranes for typically for MBR, with, of course, then significant higher flux. We had there the creation of the spin-off Bluefoot membranes in 2017. They're doing very well. They have 35 employees. There are a lot of operational installations, and they just got a very prestigious prize last year. So that's a bit how we deal with synthesis of membranes at Phyto. Now let's have an example of use of membranes, and I dig in here a bit deeper into a project that is still running. It's now in the last 6 months. And it's dealing with re-refining of used lubricant oil. The project is called Kumiri, nice consortium. And used lubricant oil is actually very well collected, especially in Europe. And a big part of it, 1 million ton each year, is re-refined, mainly by distillation now, by 27 refiners in Europe, bigger and smaller ones, deliver again clean oil that can be used again to make to make pure lubricant oil again that can be reused. Now, if you look to what is in this used lubricant oil, like you see, it's of course nicely black. And like it comes out of your car when you replace the oil. What's in it is, of course, the base oil that is typically used to make these lubricants. And there are also a lot of additives in lubricants oil. These additives, of course, give you the lubrication effect, but also they avoid the wear and corrosion. These additives are typically surfactant-like molecules, like you see here, and they contain typically metals. These give you, of course, a lot of impurities in the stream, and there are also minor impurities coming from the use, which is water, diesel, and naphtha. Of course, lubricant oil in itself is very viscous, but if you have this dirty oil, it's especially viscous. And we talk here about kinetic viscosities, 50 centistokes at 40 degrees. So it's really challenging, and that's, of course, where we think of using membranes at higher temperature, and particularly ceramic membranes. Of course, the idea is to remove everything that doesn't need to be there and end up with nice color, brownish colored base oil. Now, typically, such a re-refining process currently is done with evaporation or a lot of distillation processes. It's a quite tedious distillation. Often there is a pre-treatment before to remove the water, and often there is a post-treatment with with hydrogen to remove the last bits of sulfur. We in this project of Kumeri, we work together with a French company, Ossilup. It's located in Le Havre. It's actually a collaboration between Veolia, that are the collectors of the waste oil, and then Total, that can use the refined oil to make new lubricants. They you see their process here, and it's a three-step distillation with the first column at relatively low temperature to remove the water, then the second column to remove the diesel already at 260 degrees, and then the last column, the real column, giving you the removal of the impurities, which is at under vacuum and at 350 degrees. This gives you, of course, the base oil, and on the other side, on the bottom, it gives you a roofing type of material, so really very viscous material. They're one of the bigger refiners in Europe. Now, for us, of course, we want to find an alternative with ceramic membranes. In the beginning, we thought of this process. Maybe we still need a water remover or any other pre-treatment. And then, of course, ceramic membranes, you have to remove most of the metals and to create here also this asphalt-like retentate, and then a polishing step by membrane extraction. Of course, by this, we would be able to remove, to reduce a lot of the energy use. The first thing, we did a few experiments. We had some experience there, but very in the beginning, in the first 6 months of the project, we already performed a preliminary economic evaluation. That is very interesting to do this. So we, of course, compared our Ossilup process. We had very good information from the company, and then our targeted process. And of course, we looked at the capex cost, investment cost, and the operational cost, and we saw very quickly, but that's not so very strange, that of course it's cheapest when you don't have to do any pretreatment. And then when this is possible to remove this, you have a capex cost that can be like 2 times lower than the benchmark, while the OPEX cost is about the same. And it's actually driven by this blue part here, and this blue part comes from the cost that Ossilup, from the cost of the used oil. So Ossilup has to pay Veolia to be able to work with the collected oil. Now, of course, you put in membrane fluxes, membrane transfer coefficients that are from the first, that you get from first experiments, but it's a bit a question mark where you're going to end up. And to cover this, you actually do typically a sensitivity analysis. We did this here for membrane lifetime, and for the UF flux, you see the black costs is here the cost without any pre-treatment. Others are with pre-treatment, and the blue line is the benchmark cost. So you can see that as long as your membrane has a nice lifetime, preferably longer than 5 years, is very fine. It's not necessary that it is 10 years, 20 years, because the cost doesn't change a lot here. Also, in view of flux, it gives you a target that your membrane flux doesn't need to be much higher than 15 LMH. Um, so this or kilogram in this per hour per square meter. So these things is very interesting to get some targets for your membrane, even when you start such a project. And we had actually particularly a specific PhD which did only economic evaluation for membrane extraction in three very different applications. She has made three papers about this. You can find the solutions there. It's very interesting what can come out of a very early economic evaluation in view of membrane targets, material targets. So I would recommend it. Now, let us dig a bit into the screening. So what we want to do is screening here, of course, UF, for the UF process. And we did the screening really very, very broad with different pore sizes from 5 to 100 nanometer, different materials. And we put a lot of graftings with and without graftings. We work together with Fraunhofer, we did selenation. We did, of course, Grignard, phosphonic acid. We know from the heart we can do also. And we have a second generation of grafting, is polymer brush grafting. So he used all this to have really a huge amount of membranes, which we tested all at 110, 120 degrees. Of course, then your loops have to be very good isolated, otherwise you cannot keep this. We're working on a paper. It will be submitted very soon on the full results of this screening. Now, in this screening, we already did also a few parameter changes. We saw that it's very interesting, of course, to increase the temperature, and it fits this line you see here. It fits with the viscosity drop of the permeate, which is very different than of the feed. Typically, you're used to use the viscosity of the feed change. Here, this is very different. And we saw, of course, that there is a limiting flux. You have some kind of cake layer formation here. And it's also valuable to increase a bit the cross-flow velocity. And this evolution is following actually the laminar flow behavior. Very similar for all membranes. And this knowledge can be, of course, used to simulate, to model the process. And you see here what a permeate quality is like. See a lot of parameters here. First, the water content, viscosity, acidity number, oxidation, nitration level, diesel, naphtha, and then all metals that you can find in this string, divided in additive metals, fouling metals, from, for instance, sand, silicon, and then everything that can come out of the motor, aluminium, iron, these type of things. So in blue, you see the feeds. In orange, you see the permeate of the 10 nanometer native membrane in this case. And then in green is the product of Ossiluc. So this is our goal. You see that the UF is actually doing a very, very good first purification. And unexpected, we had a lot of water removal. And the water is probably complex, emulsified. It's not very clear in this stream, giving us this over 90% retention. All other parameters, you see a very nice removal, become very close to the goal. Of course, diesel and naphtha are not removed. And then in view of metals, we remove a lot of them, except for these with an arrow. And especially sulfur is probably very small molecules, and it's impossible to remove with UF. Of course, the next step is when we know this is working well, we go again to proof of concept of the full process we want at bigger scale and use for that multi-channel membranes and bigger installations. And we did this with about 6 type of membranes, the full concentration track up to about VCF3, which is the maximum you can get. There is about 70% of base oil in the stream. And then we saw that actually once you keep these 2 meters per second, very important in this particular case, your flux decline is actually not very big. And you can even fit this, it's consistent with film theory. And you see it here that it gets an evolution. It follows ln VCF. And you can, if you are interested in details, there is a public deliverable in Cumeri where you can find the details. Now, the other graphs give you the permeate quality. Of course, the blue stick here is again our feed. The other sticks are the permeate quality at different levels of concentration. And you will see that it stays quite nicely constant. It's also very similar for all membranes. And of course, in the end, we have a retentate that is enormously viscous, where you need to keep your high temperature to get it out of the unit. And it's the water content you find in the retentate is consistent with our 90+% retention of water. So, okay, this is the UF process. We have a polishing step after that, which is ME. Of course, we did screening first too. Screening in that case is liquid-liquid extraction tests on the UF permeate that we made in this concentration tests. And yeah, a lot of solvents are possible. Very interesting are ethanol, NMP, DMA. And we saw actually that there is a very nice correlation with the Hansen parameters and the extraction efficiencies. And if you're very high in extraction efficiency, you also have decoloration, nice decoloration. So also you form in most cases, you form very strong emulsions, very difficult to phase separate. So using a membrane in the process is very advantageous. And of course, for membranes, we go for hydrophobic membranes made by silination by our Fraunhofer partners. And we work with 100, 200 nanometer membranes there. We have also, we are very happy to have Basel high school there, and they've done a lot of testing also in for membrane extraction, and they have tested over 14 days the very robust process with ethanol at, in this case, of course, relative low temperatures. The extraction, transfer coefficient is then relative low, but by now we know we can increase this by using higher high boiler solvents, of course, and using much higher hydrodynamics. Now, as we always do, we want to pilot this, and we are doing this right now. We use for that one of our high temperature pilots that can work until 130 degrees. We adapted a bit. In this way that we have now a back pulse possibility on extra on the pilot. And this we can use this backflush instrument also to use it as the extractant loop of the ME. So it gives us a possibility also to test both UF and ME. You see here we chose for 8 multi-channel membranes for the UF part, having 2 square meter of membranes, and then a 37 single tubular module for the ME part. You see nicely how after testing at Vito, we transported to Osselup, and that's where it is located there. You see a few pictures here. And then we have been actually doing 2 months, it's finished now, 2 months of UF piloting with native 10 nanometer membranes. And we see here actually that we have found that everything we saw at lab scale and at intermediate scale comes back. So it's nicely reproduced, confirmed. You see the flux here in red at 120 degrees and in blue at lab scale. Also, the results here from the permeate quality is very, very similar to what we found at lab. And the very positive thing is, of course, now we had a very good option. We can do some things at lab, but it didn't work well with this stream. But now with the pilot, we have been able to use the back pulse. And you see when we don't use it, you have the drop at a small flux drop like we saw it at lab scale. But if we use the back pulse, we can keep the flux very stable. It's also very long stability of the flux in isoconcentration modus. We could restart with a new batch of ULO after just a short permeate rinse, so there is really no big falling issues. It's an extremely robust process. We can conclude this. And ME piloting, this is going on right now, and we will, of course, present the results later on in other presentations. So we had a synthesis project idea, project presentation. We had a presentation of an application project. Let's now look what we do right now at Vito on prediction. And then, of course, we all know we learned, I think lots of us learned a lot on OSN, but not to this level to predict the OSN process. And then, like also Georgie and his team is doing at CAUS, we look at data-driven modeling here. And of course, we want to use the extensive data we have at Vito in order to, on one side, get rid of the very intensive membrane screening and time-consuming screening, but also in the other way around, to be able to define the best membrane with the best chemistry for a particular separation. Now at Vito, our data, especially in solvents, we have a lot of ceramic data. And the good thing about data sets from ceramic membranes is, of course, that these membranes are not swelling. So meaning that there is, let's say, one effect of OSN of the solvent that is not there. So I always looked at it when somebody can disentangle what is happening here. The ceramic data is very important, or can really help here. Of course, we characterize the solvent, the solute, and the membrane and the test conditions by different parameters, like we all do. And we compared a bit the CAUS database. I didn't look yet at the database from Leuven, the bigger database. And you see here the CAUS database in blue and the Vito database in red. So in general, we have actually our ranges of parameters are in general bigger. This is, of course, because I think ceramics are, and with grafting, we are more to the polar side and intermediate polarity side, and a bit like I mentioned in the beginning in the questions of Georgie, we are a bit on the higher pore size compared to the polymeric membranes. But it's also because I think also because I'm a physicist, I'm working also together with the University of Hasselt here, which are physicists working with me. We include water, and not only water, but also water solvent mixture. For us, this is just another solvent, and a good model should be able to include everything. Okay, you can see some of the background in Peter Jan's first publication. What he is doing is looking at different type of modelings, not only statistical modeling, but also hybrid modeling and full machine learning AI modeling. I show here some of the results that he recently published. And we focused here on results of NF membranes, 0.9 nanometer, titanium membranes, 450 Daltons, native and C1 grafted with our ring-hour grafting method. And we looked first statistically to the results. You see here the correlation between flux and flux times viscosity. Flux times viscosity are the higher bars as function of different aspects, different parameters, different solvent parameters, solvent characteristics. And actually, what we see is there are huge correlation coefficients. Actually, solvent has a huge influence on the flux. Not only you see here a lot of polarity characteristics, but also the size of the solvent is quite important. And what we see also is, of course, if you take out already one part of the viscosity effect by multiplying flux by viscosity, correlations get higher. And the correlations for a grafted membrane are really much higher than for native membrane, meaning actually that for the flux is almost only defined by the solvent, while for the native membranes, solute has also a big influence. And this is all to do with the better affinity of our grafted membranes to the solvent, but also to the diminished interactions with the solvent by using particularly this C1 grafting, something we saw also in the fouling studies. Also for retentions, we looked at correlations, and in general, they're much lower, but they're higher in this case for the native membranes than for the grafted membranes. Even when you look to scatter plots here of these retentions as function of flux, you clearly see it's all over the place for native, not a lot of correlation there. And it's very systematic for the grafted membranes. Also here, we believe this has to do with decreasing interactions with the solutes. When you dig a bit deeper, we have been, and it's often used for ceramic membranes, the Spiegel-Kedem theory gives an interesting way to look at the results. And we see here that we can actually model this behavior for the grafted membrane with only one parameter varying. We looked, of course, to molecules here that are bigger than the pore size of the membrane. So for these molecules, sigma is 1, and there is only this diffusion parameter here, which is varying for different solvent-solute mixtures. And while for native membrane, both parameters are important and are dependent on the mixture. Of course, we looked already at the full machine learning and AI modeling. We trained with all the data we had, and we defined, we did new experiments with new data, and we got some new data, and you see that there is a quite nice prediction 81% accuracy here. Now, Peter Jan is working on hybrid modeling, different ways of hybrid modeling, including physical constraints of the full AI in various ways and looking to the differences between the results. And the paper is also here in submission phase. So this is definitely going on further. We will elaborate much more on this later. So this brings me actually to the end of my presentation. I think I could show you that doing applied research, working with company comes with its own rules, dynamics, and challenges. Typical aspects are you need experimental feasibility with real streams in real conditions with commercially or on-scale available membranes. You need a proof of concept of the full process at scale where you have all things included, like the potting material or the O-rings for sealing of ceramic membranes. Very good to have economic feasibility also, and to be able to show the long-term process robustness at pilot scale. Process modeling and predictability is also an extra asset. And we're working more and more on this aspect. So with this, I, of course, have to thank all past and current team members. And of course, I have to, my experience extends, of course, a lot of Belgium, especially also Netherlands and EU projects. And I've had many collaborations with academic and industrial partners. They're all very thanked very well. With this, I also have to thank you for your attention.
Anita, thank you very much for your inspiring presentation. It was nice to see from an industrial perspective how membranes are applied and what are the challenges. There are a couple of questions on the chat, so let's go through them one by one. First question, for pharmaceutical applications, what is preferred in the industry, ceramic or polymeric membranes?
Well, our experience is actually that they have a preference for ceramic. I don't say this is a general thing. I cannot say, but the project we had with the companies we have been collaborating, they know ceramic materials a lot from chromatography, often silica-based materials, and they like the robustness and the fact that it doesn't leach. Of course, when you use ceramic, in many occasions we had to show that there is no leaking. We even did at Vito a lot of effort to do the testing like you would do to get a food certification stamp, or even FDA approval stamp. So, but it's quite easy to do for ceramics. And it turned out in some project that it was an issue, this leaching, for even the OSM, commercialized OSM membranes. And the fact that there is not an FDA thing, but it's very difficult, and it's case by case up to now. I guess this is one of the reasons why Evonik took away some of their membranes from the market. But there, I think, actions going on to get some kind of certification label on some membranes that are general, that are not case to, that you don't have to do the approval again, case by case. That's our experience, actually.
Okay, so the main advantage for the industry is the leaching or not having a leaching from the ceramic membranes.
And then actually, I must say, and I think this is one of the, in my point of view, very big plus of the ceramic membranes is the fact that we have a universal potting. Potting, the sealing in a ceramic module is done by a glass sealing on the, or even can be even a PTFE sealing on the end of the membranes and O-rings on top of that.
Mhm.
These have been shown to work for everything. They don't give you any issues. Of
Okay.
course, in some solvents, you really need the colorless O-rings. Expensive. Huh? This is expensive. But the potting of polymeric membranes is also a weak point, I think. Not only for the leaching, but the fact that it's also case I good for specific ranges of solvents. Varieties of solvents have maybe their own potting, and that's I think also a good point for the ceramics.
All
So
right.
it's from the pore fillers of the membrane and the membrane materials itself, but it's also can be also leaching and stability issues with the potting.
Okay. Now moving on to the second question. What is the major limitation, if any, to work on flat sheet membranes for Grignard grafting membranes instead of tubular membranes?
In process wise, there is no issue. We can do this. What we use, how we work, is we use actually the module of the membrane as the reaction vessel. That's how we do it at Vito. Um, the spin-off is thinking, yeah, in another way maybe, but it's also related. So in principle, if you have a module for your membrane, for your flash heat membrane, you can use it in the process. It's even, we put it with flexibles in our systems. It's possible to use. The thing is that at least for ceramic NF membranes, the the NF, at least that we don't use them anymore. So maybe there have been some for quite a long time. So maybe there has been some evolutions, but at least the flat sheet NF membranes that I know from before, they have a lot of carbon in there to get the sticking of the NF top layer to the intermediate layers. And this makes that your anchor points for your Grignard, the OH groups, are different. The amount is different, the availability is different. So that's the main reason why I don't like to work with flat sheet. But I must say there are, of course, open ceramics flat sheet, like for the discs for the rotational instruments. There are this nice flat membranes with these holes in it, flat sheet. Think they're not available in these very small pore sizes, or they're in evolution. I think we have some project proposals now to look at Grignard grafting there. So we will do some things but then these membranes are again commercial membranes and not just small membranes that are made by the companies for some fundamental studies. These big rotational discs, for instance, these are the sizes made for commercial use.
I think that answers the question. So there are two more questions to go through. What is the story behind the naming of the membrane Fun Mem?
Yeah, It's functionalized membranes, but the name by the spin-off, it's not used anymore. He likes to use it to give his technology the name Graftech, coming from grafting. FunMem has, for people who speak Dutch, it seems a very strange and funny side effect. So, and he uses also the spin-off is called A membranes because, and the A then stands for affinity. So FunMem is a name that we still use and that I keep sometimes in my presentations because some slides have been made a long time ago, but it's not used anymore. It's an internal name for the moment.
Okay, okay. And the final question is about the transport properties in the fabricated membranes. So any values for those transport properties like thermal conductivity and mass diffusivity?
Yeah. Um, yeah, that's of course more difficult to know. What we have been doing in the past, and we should dig a bit deeper into the. We're planning to go deeper into this. We, I'm a big fan of Hansen parameters. I think Georgie, you know.
I do.
I've seen a lot of usefulness, available use of them uh, to catch all interactions possibilities. It catches this. We have been uh, uh, calculating or having the high space measured for powder material, native and grafted. It catches. It's complex because with the Grignard grafting, we have not a full coverage. We have an partial coverage. And we see, actually, with the grafted powder, we see still the OHs that are there. And we see actually when you uh, have these 3D plots, we have two spheres, one around this OH polar part, and then one around the group, the HSP of the group we have put there. But we want to dig in a little bit deeper to confirm this with other modifications. And we plan to use actually these also in the modeling. For the moment, it's not yet done. What we use is what we can measure, like the contact angle.
Mhm.
But this definitely doesn't catch everything. And I've tried also in Kumeri the results of all these crafted membranes to use the high space of the crafted membranes. In this particular case, it didn't bring me very far, but yeah, it's something like thermal conductivity. Yes, we don't know, or we have to find a way to measure it.
Right. I'm looking at the chat, but there are no more questions. But I'm sure that everyone knows how to reach you in case they have further questions in the future.
Very good. And not me alone. I have gray hair enough to come close to my retirement. I will be normally there still in 26. I work now 50%, but my colleagues, senior researcher colleagues like Peter van der Zanne, Dominique Ormerod, Chris de Sitter, Fadi Nari, Nara, they're all there also to answer questions.
Great, thank you very much. I think we all enjoyed your presentation and all the work that you presented from the past decades, I would say. You covered quite a lot. So thank you very much for accepting our invitation and being here today. We really appreciate it. And
Okay, it was
thank you,
pleasure.
Anita.
What's mine? Thanks, Georgie.
Thank you. Take care.
Okay.
Bye, everyone.